Oh, one thing I want to point out is look at Sticky Bot. You see something on it. It's not just to look like a gecko. It has a tail. And just when you think you figured out nature, this kind of thing happens. The engineers told us for the climbing robots that if they don't have a tail, they fall off the wall. So what they did was they asked us an important question. They said was, well, it kind of looks like a tail, even though we put a passive bar there. Do animals use their tails when they climb up walls? What they were doing is returning the favor by giving us a hypothesis to test in biology that we wouldn't have thought of. So, of course, in reality, we were then panicked, being the biologist, and we should know this already. We said, well, what do tails do? Well, we know that tails store fat, for example. We know that you can grab onto things with them. And perhaps it's most well known that they provide static balance. It can also act as a counterbalance. So watch this kangaroo. See that tail? It's incredible. Mark Rapert built a Uniroo hopping robot, and it was unstable without its tail. Now, mostly tails limit maneuverability, like this human inside this dinosaur suit. My colleagues actually went on to test this limitation by increasing the moment of inertia of a student, so they had a tail, and running them through an obstacle course and found a decrement in performance, like you'd predict. But of course, this is a passive tail, and you can also have active tails. And when I went back to research this, I realized that one of the great TED moments in the past, from Nathan, we talked about an active tail.
Myhrvold thinks tail-cracking dinosaurs were interested in love, not war.
We talked about the tail being a whip for communication. It can also be used in defense. Pretty powerful. So we then went back and looked at the animal, and we ran it up a surface, but this time what we did is we put a slippery patch that you see in yellow there. And watch on the right what the animal is doing with its tail when it slips. This is slowed down 10 times. So here's normal speed, and watch it now slip, and see what it does with its tail. It has an active tail that functions as a fifth leg, and it contributes to stability. If you make it slip a huge amount, this is what we discovered. This is incredible. The engineers had a really good idea. And then, of course, we wondered, okay, they have an active tail, but let's picture them. They're climbing up a wall, now imagine, or a tree, and then they get to the top, and let's say there's some leaves there. And what would happen if they climbed on the underside of that leaf, and there was some wind, or we shook it? And so we did that experiment that you see here, and this is what we discovered. Now that's real time, you can't see anything, but there it is slowed down. What we discovered was the world's fastest air writing response. For those of you who remember your physics, it's a zero angular momentum writing response. But it's like a cat. You know, falling cats do this, they twist their bodies, but geckos do it better, and they do it with their tail. So they do it with this active tail as they swing around, and then they always land in sort of Superman skydiving posture. Okay, now we wondered if we were right, we should be able to test this in a physical model, in a robot. So for TED, we actually built a robot over there, a prototype, with the tail, and we're going to attempt the first air writing response in a tail with a robot. If we could have the lights on it. Okay, there it goes. And show the video. There it is. And it works just like it does in the animal. So all you need is a swing of the tail to right yourself. Now, of course, we were normally frightened because the animal has no gliding adaptation, so we thought, oh, that's okay, we'll put it in a vertical wind tunnel. We'll blow the air up, we'll give it a landing target, a tree trunk, just outside the plexiglass enclosure, and see what it does. So we did, and here's what it does. So the wind's coming from the bottom, so slow down 10 times. It does an equilibrium glide, highly controlled. This is sort of incredible, but actually it's quite beautiful when you take a picture of it. And it's better than that. It just doesn't glide, it maneuvers in midair. And the way it does it is it takes its tail and it swings it one way to yaw left, and it swings its other way to yaw right. So it can maneuver this way. And then, we had to film this several times to believe this, it also does this. Watch this. It oscillates its tail up and down like a dolphin. It can actually swim through the air. But watch its front legs. Can you see what they're doing? What does that mean for the origin of flapping flight? Maybe it's evolved from coming down from trees and trying to control a glide. Stay tuned for that. So then we wondered, could they actually maneuver with this? So there's the landing target. Could they steer towards it? With these capabilities, here it is in the wind tunnel. And certainly looks like it. You can see it even better from down on top. Watch the animal. Definitely moving towards the landing target. Watch the whip of its tail as it does it. Look at that. It's unbelievable. So now we were really confused because there's no reports of it gliding, so we went, we have to go to the field and see if it actually does this. Completely opposite the way you'd see it on a nature film, of course. So we wanted to do, they actually glide in nature? Well, we went to the forests of Singapore and Southeast Asia. And the next video you see is the first time we've showed this. It's the actual video, not staged, a real research video, of an animal gliding down. There's a red trajectory line. Look at the end to see the animal. But then as it gets close to the tree, look at the close-up and see if you can see it land. So there it comes down. There's a gecko at the end of that trajectory line. See it there? There. Watch it come down. Now watch up there and you can see the landing. Do you see it hit? It actually uses its tail too, just like we saw in the lab. So now we can continue this mutualism by suggesting that they can make an active tail. And here's the first active tail in the robot, made by Boston Dynamics. So to conclude, I think we need to build biomutualisms like I showed that will increase the pace of basic discovery and their application. To do this, though, we need to redesign education in a major way to balance depth with interdisciplinary communication and explicitly train people how to contribute to and benefit from other disciplines. And of course, you need the organisms and the environment to do it. That is, whether you care about security, search and rescue, or health, we must preserve nature designs. Otherwise, these secrets will be lost forever. And from what I heard from our new president, I'm very optimistic. Thank you.
Tot rău spre bine, văzusem alt clip anterior ăstuia cu același individ și pe ăla speram să-l găsesc, dar ăsta cred că, deși a fost mai puțin haios ca primul pe care l-am văzut, mi-a deschis mai multe la fileu, ca să zic așa. Aș puncta puțin aici ideea de transdisciplinaritate, de integrare între domenii de specializare și de deschidere, dar și de nevoia de a transforma modul în care facem educația pentru a avea oameni capabili să facă acest ping-pong între două, să spunem, domenii de activitate, de cercetare, de știință complet diferite. Și de asemenea, tot în același spirit, am să o caut și pe doamna de aici, Janine, să vedem dacă o găsesc. Janine, da.
And I'm also thrilled to, at a conference that's devoted to Inspired by Nature, you can imagine. And I'm also thrilled to be in the foreplay section. Did you notice this section is foreplay? Because I get to talk about one of my favorite critters, which is a western grebe. You haven't lived until you've seen these guys do their courtship dance. I was on Bowman Lake in Glacier National Park, which is a long, skinny lake with sort of mountains upside down in it. And my partner and I have a rowing show. And so we were rowing, and one of these western grebes came along. And what they do for their courtship dance is they go together, the two of them, the two mates, and they begin to run underwater. They paddle, I think sort of, and started to, life has a lot to teach us, but what I'd like to talk about today is what life might teach us in technology and in design. What's happened since the book came out, the book was mainly about research in biomimicry, and what's happened since then is architects, designers, engineers, people who make our world have started to call and say, we want a biologist to sit at the design table, to help us in real time, become inspired. Or, and this is the fun part for me, we want you to take us out into the natural world. We'll come with a design challenge and we find the champion adapters in the natural world who might inspire us. So this is a picture from a Galapagos trip that we took with some wastewater treatment engineers. They purify wastewater. And some of them were very resistant, actually, to being there. What they said to us at first was, you know, we already do biomimicry. We use bacteria to clean our water. And we said, well, that's not exactly being inspired by nature. That's bioprocessing. You know, that's bioassisted technologies. Using an organism to do your wastewater treatment is an old technology called domestication. This is learning something, learning an idea from an organism, and then applying it. And so they still weren't getting it. So we went for a walk on the beach. And I said, well, give me one of your big problems. Give me a design challenge. Sustainability speed bump that's keeping you from being sustainable. And they said scaling, which is the buildup of minerals inside of pipes. And they said, you know, what happens is mineral, just like at your house, mineral builds up and the aperture closes and we have to flush the pipes with toxins or we have to dig them up. So if we had some way to stop this scaling, and so I picked up some shells on the beach. And I asked them, what is scaling? What's inside your pipes? And they said calcium carbonate. And I said, that's what this is. This is calcium carbonate. And they didn't know that. They didn't know that what a seashell is, it's templated by proteins, and then ions from the seawater crystallize in place, okay, to create a shell. So the same sort of a process without the proteins is happening on the inside of their pipes. They didn't know. This is not for lack of information, it's a lack of integration. You know, it's a silo, people in silos. They didn't know that the same thing was happening. So one of them thought about it and said, okay, well, if this is just crystallization that happens automatically out of seawater, self-assembly, then why aren't shells infinite in size? What stops the scaling? Why don't they just keep on going? And I said, well, in the same way that they let go of, that they exude a protein and it starts the crystallization, and then they all sort of leaned in, they let go of protein that stops the crystallization. It literally adheres to the growing face of the crystal. And in fact, there is a product called TPA that's mimicked that protein, that stop protein, and it's an environmentally friendly way to stop scaling in pipes. That changed everything. From then on, you could not get these engineers back in the boat. The first day, they would take a hike, and it was click, 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 click. 5 minutes later, they were back in the boat. We're done. You know, I've seen that island. After this, they were crawling all over. They would snorkel for as long as we would let them snorkel. What had happened was that they realized that there were organisms out there that had already solved the problems that they had spent their careers trying to solve. Learning about the natural world is one thing. Learning from the natural world, that's the switch. That's the profound switch. What they realized was that the answers to their questions are everywhere. They just needed to change the lenses with which they saw the world. 3.8 billion years of field testing. 10 to 30, Craig Ventnor will probably tell you, I think there's a lot more than 30 million well-adapted solutions. The important thing for me is that these are solutions solved in context. And the context is the Earth, the same context that we're trying to solve our problems in. So it's the conscious emulation of life's genius. It's not slavishly mimicking, although Al is trying to get the hairdo going. It's not a slavish mimicry. It's taking the design principles, the genius of the natural world, and learning something from it. Now, in a group with so many IT people, I do have to mention that what I'm not going to talk about. And that is that your field is one that has learned an enormous amount from living things on the software side. So there's computers that protect themselves like an immune system, and we're learning from gene regulation and biological development, and we're learning from neural nets and genetic algorithms, evolutionary computing. That's on the software side. But what's interesting to me is that we haven't looked at this as much. I mean, these machines are really not very high tech in my estimation, in the sense that there's dozens and dozens of carcinogens in the water in Silicon Valley. So the hardware is not at all up to snuff in terms of what life would call a success. So what can we learn about making not just computers, but everything? The plane you came in, cars, the seats that you're sitting on. How do we redesign the world that we make, the human-made world? More importantly, what should we ask in the next 10 years? And there's a lot of cool technologies out there that life has. What's the syllabus? 3 questions for me are key. How does life make things? This is the opposite. This is how we make things. It's called heat, beat, and treat. That's what material scientists call it. And it's carving things down from the top with 96% waste left over and only 4% product. You heat it up, you beat it with high pressures, you use chemicals. Okay, heat, beat, and treat. Life can't afford to do that. How does life make things? How does life make the most of things? That's a geranium pollen, and its shape is what gives it the function of being able to tumble through air so easily. Okay, look at that shape. Life adds information to matter. In other words, structure. It gives it information. By adding information to matter, it gives it a function that's different than without that structure. And thirdly, how does life make things disappear into systems? Because life